All right, as usual, let me begin with asking whether there are any questions. Now, we've just been talking for about 10 minutes here before the tape went on, people asking me questions. So there must be some questions. Yes, okay. So the questions have to do with the homework, no doubt. Okay, go ahead with your question.
How can we determine the simulation result of?
So remember, you got two columns, 4 columns actually. You've got the distribution function of W, and you've got the distribution function of R. Now, what this means, that's the probability that W is less than or equal to T. And this is the probability that R, which is actually W plus X, is less than or equal to T. And then coming down here, you've got different values of T. And here you have 2 columns. One is theory, and one is simulation. Theory, simulation. Now, for the theory, you have a formula for this. What you have to know is you have to know how many servers there are. Well, we said it was MM10. So that means it's an Erlang delay model with 10 servers. And we said that the order of service is FIFO. So that means, because we derived in class, that the probability that the waiting time is greater than T is equal to the Erlang C value times e to the minus 1 minus rho S mu T. That's the general formula. So that's going to allow us to calculate the theory here, except that this is greater than, this is less than or equal to. So the column here is 1 minus the values you compute here. The T values are the values given here, and since they're measured in units of average service time, that's the same thing as taking mu equal to 1. Then S is going to be 10 because it says 10 servers, and rho is going to be 90% because it tells you that the utilization is to be 90%. So that means that if the mu, which is the reciprocal of the average service time, is 1, then the lambda must be, that means that if the utilization is 90%, you must be offering 9 Erlangs, and the number of Erlangs is the arrival rate times the average service time. So if the average service time is 1, the arrival rate must be 9. So you put in that and into this formula, and you calculate these values according to this. Now the simulation you already have. I gave you the code for that, except that I said when I gave it that I wasn't sure it was correct because the last time I used it, there seemed to be the answers weren't close enough between simulation and theory, and I thought that was because of some parentheses that were missing in an if statement. And so I wanted you to check out whether or not that was correct. But what I'm hearing from you is that you're all getting very close agreement between these 2 columns. Is that true? Okay, but remember now, this is theory, this is simulation. These are independent of each other. They have nothing to do with each other, except that the parameter values are the same. And of course, when you give parameter values that are supposed to give you a rho of 90%, then you won't get exactly 90% in the simulation, although it should be very close. Okay, now over here. Now there's 2 things. You've got to augment the theory yourself, and you have to change the simulation code somehow. Now the theory is simple. I gave you the formula, which is that the distribution function, let's see, I think this is what I said. This is the probability the response time is less than or equal to T. So it's the probability the sum of the service time and the waiting time is less than or equal to T. So I'll take here the distribution function of the service time with, let's call this U. I can't call it the same, use the dummy variable, the parameter T. So let's call it U. So if I differentiate that, take its differential, or equivalently the density function of the service times, then this corresponds to the probability that a service time is equal to u. So for the response time to be less than t, then I'm going to multiply that by the distribution function of the waiting time evaluated at t minus u, and then integrate that as u varies from 0 to t. And that should describe the distribution function for t greater than or equal to 0. Now you know what this is because you've already got that over here. So you plug this into the formula, you get some answer, and then you just plug it in numerical values of t just like before, and you're going to get values here. And for example, as a key, sort of obvious, that this value right over here should be 0 because since the response time is the sum of the waiting time plus the service time, even if the waiting time is 0, which occurs with a positive probability, the service time will not be 0. That is, it's possible, but the probability the service time is 0 is 0. So what this should mean is that everybody's, nobody has a response time that's equal to 0. Okay, so that's, theoretically, that's a check. And of course, the simulation should give you the same answer. All right, now in the simulation, what you have to do is in the process of the simulation, you already calculate W and you already calculate X. And to calculate this column here, what you had to do was you had to, for each customer, you had to take the value of his W, and you recorded all the W's, and then you took the fraction of those W's that are less than or equal to each of these T's. All right, now you do the same thing to get the response time, except that with the response time, the thing that you are comparing with the T is not the W, but the W plus the X. But make certain, when you add these two things up, that for each individual customer, this is his W plus his X. Don't use the X of the previous customer, because that will already have been included in the W, and then these things won't be independent. So when a customer arrives, he waits, and then after he waits, he enters service. Now, if he waits 0, that is, if he enters service immediately, then his response time is his service time. And if he does not enter service immediately, then his response time is how long he waits plus how long he spends in service. So in principle, this should be easy. Okay, does this answer your questions? I can't tell you exactly how accurate the simulation should be, although I think it should be fairly accurate. How many customers did you run it for? I asked you to run it for at least 100,000, but if you could do 1,000,000. 100,000. Okay, for 100,000, am I correct to say that you all get good agreement between theory and simulation for this? So the only problem that you're having, if you have one, is over here, right? Okay, so the agreement between theory and simulation here should be of the same level of accuracy as the agreement here. So if they're different, if these two columns are a lot different and these are very much the same, then at least one of these is wrong. Yeah. Right.
If mu equal 1, I calculated that the rho is 95%. So
the rho is 95%.
Yeah, 95. Because
Oh.
the rho is 90 and the lambda is 4, so the mu is 4/9.
Wait.
Calculate that, so I get the same, almost the same, the theory and the simulation.
What I didn't say here, I just said 90% server utilization. I didn't say what the lambda and the tau are. Right? The rho, let me know if I'm answering your question. Okay? I think so. The rho is equal to the carried load divided by the number of servers. And the carried load is the offered load if A is less than S. Okay? So that's going to be the arrival rate times the average service time divided by the number of servers. Or since mu is the reciprocal of the average service time, that's just a definition, then it's equal to lambda over S mu. All right, now in your case, S is 10 and rho is 90%. In other words, you're asked to do it for utilization of 90%. So that means that if you take mu to be 1, so if mu equals 1, then lambda must equal 9. Okay, now if you chose a different lambda and a different tau whose product still turned out to be 9, right? I could pick tau is equal to 2 and lambda is equal to 4.5. That would not affect the Erlang C value, but it would affect this part over here. But then, of course, if I did that, then since I said that this t is measured in units of average service time, then 1 second of average service time, if my tau is 2, would be 2 seconds. So I would have to adjust the t so that mu t is the same value as before. In other words, if you had the simulation and you had as your input values the mu and the t, then you could put in any values you want. But then you would also have to specify what the units of the t's are. Are they seconds, minutes, hours? So typically what you do is you say, I'll just take the unit of service time as the average service time. So whatever tau is, I will call that 1 unit. And then you measure t in those units. So if tau is 2 minutes, then when t is equal to 1, that means 2 minutes. 1 unit of time would be 1 service time, which would be 2 minutes. So the way you do that in the program is and in the calculation, is you simply set the mu equal to 1, and then t is measured in units of average service time. It's just a scaling. Okay? Anything else here? Yes.
When we count the waiting time, it's just like a probability of W greater than T.
Mm-hmm.
In the simulation, we just using the number of customers, the W greater than T over total number of arrivals.
Mm-hmm.
Right.
Right.
But in the for the response time, I'm not sure. Is it we just count the number of customer whose W plus X greater than T?
Mm-hmm. Right.
The number of this and over the total.
Right. The denominator is the same. It's the total number of customers.
Yeah.
But the response time, instead of being just the W, is the W plus the X.
Plus X greater than T. We just count this kind of how many customers.
Right.
Is it right?
Sounds right to me. There's no hidden trick here that I know of. This should be straightforward. Tricks will come later in the course. This should be easy. And programming is always tricky, I guess, but there's no hidden bomb here. Okay, in the homework? So we're ready to go on to the next topic, is that right? Okay, let's make the homework due nominally a week from today. All right, so if you have any problems, let me know on Wednesday. Whatever the problems are now, you should have ironed them out. Okay, now we're starting a new topic, which is Chapter 4. So I covered the stuff about quasi-random input last time very briefly. Maybe I'll go back to that later, I don't know. But right now I want to get into the multidimensional case. Now what we did before was we had systems in which we could express things by writing rate up equals rate down. For example, we'd say things like lambda sub j pj is equal to mu sub j plus 1 p sub j plus 1. And the argument there was that, well, we just imagine this diagram that shows the state diagram that shows the number of customers present as a function of time, and it simply jumps up and down or stays in the same state. The jumps are size 1. And this counts the rate at which the jumps up occur from state j. This counts the rate at which the jumps down occur from state j plus 1. And then you say the rate at which you go up from j and the rate at which you go down from j plus 1 must be equal. And that's how these equations come about. Now, a sufficient condition for being able to write these equations is that you have is that all of the underlying distributions are exponential. Okay, now this is a system in which you need only one variable to describe what's going on. But let me give an example of a system where I need more than one variable. Suppose I had something like this. Let's take, well, the simplest one-dimensional system was an infinite number of servers, like that. And customers arriving at some rate lambda and having some service completion rate mu. Well, now I'm going to imagine that there are two streams of customers. And customers from stream 1 arrive at rate lambda 1. Let's say that they have that there's Poisson input, for the sake of argument. Let's make it as easy as possible. So we have Poisson input with rate 1, and we have exponential service times with service completion rate mu1. And so the offered load then in Erlangs from stream 1 is A1 Erlangs. Lambda 1 over mu1, or lambda 1 times tau 1. And similarly, for stream 2, we have A2 Erlangs, Poisson input with rate lambda 2, which is different from lambda 1, and exponential service times with service completion rate mu2, which in general is different from mu1. Okay, so now I want to analyze this system. And I want to ask whether or not I can write rate up equals rate down. So, of course, this is general here. Let's try and specialize this to this. So first of all, I could say, well, suppose I'm in state j. What is the rate up from that state? And then you'd say, well, arrivals are occurring from stream 1 according to a Poisson process with rate lambda 1. From stream 2 with rate lambda 2, we know that if you take two independent Poisson streams, these are assumed to be independent, take two independent Poisson streams and combine them, that the combined rate is just the sum of the rates, and that the process is again a Poisson process. So if this is a Poisson stream with rate lambda 1 and that's Poisson with rate lambda 2, then the aggregate stream is Poisson with rate lambda 1 plus lambda 2. So I could write this. So this would give me the rate up from state j. Now I got to get the rate down from state j plus 1. That's the fraction of time I'm in state j plus 1. But now the question is, what is the aggregate service completion rate when I'm in state j plus 1? Well, the answer is you don't know unless you know how many customers are from stream 1 and how many customers are from stream 2. Because the aggregate service completion rate for customers from stream 1 is mu1, the service completion rate of those customers, times the number of such customers, which we don't know. We can call it J1. And similarly, for stream 2, the aggregate service completion rate would be J2 mu2. But these equations don't make sense as they stand because the J that describes the state of the system doesn't tell you how that J is made up. It doesn't tell you how much of that J is customers of type 1 and how much is customers of type 2. And by the way, this isn't even right because this J1 plus J2 has to add up to J plus 1. That is, the way I've written it is this number here plus this number here is equal to that number there. So what that means is that one variable is not enough to describe what's going on. I need two variables. What I need is to write equations of this form. Let's see, I'll write them here. OK, I'm going to erase this. And write instead for each state, rate out equals rate in, as follows. Now I'll say, I'll represent the state of the system by two variables, J1 and J2, where J1 is the number of customers from stream 1 and J2 is the number of customers from stream 2. And then I'll imagine that I have a grid like this. Let's say that this is J1 and this is J2, and here are the points on the grid. Every cross point represents a state. And then what I did before was I had a picture in which the diagram that represented the states of the system went like this, and then I simply cited and looked at, cited along here, say, and looked at the number of jumps up that I would see from between state J and J plus 1, and the number of jumps down. Here's a jump up. Sometime later there'll be a jump down. And I counted them. That's how I got the rate up equals rate down. Now, instead of imagining that I have a boundary and I go above the boundary and below the boundary, now I'll imagine that my boundary is a circle like this. And here's my state. And now I'll say what happens here is if I'm in this state, then after a while I will leave and I will go to some neighboring state. Could be any place. So there's a certain flow by which I go across the boundary from inside out. And similarly, there's a flow at which I go from across the boundary from outside in. And I say if I watch this over a long period of time, then the number of times that I leave would be approximately equal to the number of times I would jump back in. It's the same idea, except that now I have a two-dimensional picture instead of a one-dimensional picture. And so for every state, I draw a circle around that state, a boundary, and I equate the rate at which I leave that state and jump to neighboring states to the rate at which I enter the state from the neighboring states. OK, so what is the rate at which I leave this state? Well, if this is the fraction of time I'm in it, and when I'm in it, customers arrive at rate lambda 1 from stream 1 and lambda 2 from stream 2, then that is the rate. Left something out here. Then this is the rate at which I leave this state because of arrivals. But I can also leave this state because of departures. And the rate at which that occurs is for stream 1, J1 mu 1, and for stream 2, J2 mu 2. Okay, so this is the fraction of time I'm in state J1, J2, where J1 is number of customers from stream 1, and J2 is number of customers from stream 2. Both Poisson streams, but with different rates, and both exponential service times, although it turns out that that assumption can be removed. Major theorem again. And the service completion rates, which means the average service times for the two streams, are different. Like, for example, this could be voice traffic and this could be data traffic sharing the same communications channels. OK, so if there are J1 customers from stream 1 and their aggregate and their service completion rate is mu 1 per customer, then the aggregate service completion rate from customers from stream 1 is J1 mu 1, and likewise the aggregate service completion rate for customers from stream 2 is J2 mu 2. All right, now I have to equate that to the rate into that state from the neighboring states. Well, in this model, all that can happen is, well, let's see. I could be in state J1 minus 1, J2, and have an arrival from stream 1 occur. If that happens, then the number of customers present from stream 1 jumps from J1 minus 1 to J1. There's no boundary condition here. We don't have to worry about what happens to the blocked customers because by assumption, we're making things easy for ourselves by assuming an infinite number of servers. Okay, how about arrivals from the other stream? Well, I could be in state J1, J2 minus 1 and have an arrival from stream 2. The rate at which that occurs is lambda 2. Or I could be in state J1 plus 1, J2, and have a departure from stream 1. The rate at which that occurs would be J1 plus 1, mu 1. And similarly, I could be in state J1, J2 plus 1, and have a departure from stream 2. The rate at which that occurs would be J2 plus 1, mu 2. So these equations, rate out equals rate in, are analogous to the earlier equations, rate up equals rate down, except that the earlier equations were easy to solve because once you wrote them, you just solved them recursively. You got P1 in terms of P0, P2 in terms of P1 in terms of P0, and so forth. So it was easy. But here, you can't solve these things by successive substitution. You have to solve them simultaneously. So now, you might have what looks like a very difficult problem because what I have here is basically a doubly infinite set of simultaneous equations because J1 runs from 0 to infinity, J2 runs from 0 to infinity. Okay, but it turns out that in many of these cases it's easy to get the answer. And so I'm going to get the answer by an argument that has nothing to do with solving the equations. Then I'm going to take the solution, substitute the solution back into the equations, and show how the solution works, and then that's going to give us some insight into problems of this type. Okay? Everybody clear on what's happened so far, where this theory comes from? Okay, all this stuff is in chapter 4. All right, now the way I'm going to solve the problem is to say, well, I simplified things by assuming that I had an infinite number of servers, which means that the two streams never interact with each other. No customer from stream 2 is ever denied service because a customer from stream 1 is holding a server. So I'll analyze it by imagining that these things actually are separate. That is, the customers from stream 1 will take servers 1, 3, 5, and so forth. And the customers from stream 2 will take 2, 4, 6, and so forth. So obviously, the number of customers from stream 1 and the number of customers from stream 2 are independent of each other. And so the solution should look like this. It should be true that the probability that I'm in state J1, J2 is equal to the product of the marginal probabilities for each stream because they're independent since they don't interact in any way. So this should be given by P1, J1 times P2, J2, where the P1, J1 is simply the probability that in a system with an infinite number of servers and Poisson input with rate lambda 1 and exponential service times with rate mu 1, that there's exactly J1 customers present. And the same for P2, J2. Okay, but we already know what that is. We know what these marginal distributions are because we know exactly what you'd get if you offered a Poisson stream to an infinite number of servers. In fact, this is like the Erlang B model with an infinite number of servers. So what we know is that P1 of J1 is equal to A1 to the J1 over J1 factorial times P0. Now the P0 that fits here, actually I should write it as P1 of 0. Of course we know what that's going to be, but it really doesn't matter. It'll turn out that this normalizing factor is simply e to the minus a1. But it doesn't matter what it is. It's a constant. And similarly, P2 J2 is equal to a2 to the j2 over j2 factorial times P2 of 0, which of course is e to the minus a2. So therefore, the solution P of J1, J2 must be of the form A1 to the J1 over J1 factorial times A2 to the J2 over J2 factorial times a constant, the constant being that being e to the minus a1 times e to the minus a2. So I wrote the equations, but I got the solution without using the equations. I got the solution by recognizing that I had a special case here. The special case being an infinite number of servers. Since the number of servers is infinite, the two streams don't interact with each other, and therefore the number of customers from each stream should be independent of the number of customers from the other stream. And therefore, the joint probability of the number of customers from each stream should be the product of the marginal probabilities for each stream individually. So, and that is easy to get because that simply reduces to the one-dimensional case that we already had before, so we know what the answer is. So now I want to take this answer and I want to plug it back into these equations and see what happens. Now we know that if we did it right, it must be true that the sum of the terms on the right must equal the sum of the terms on the left, because that's what it means to be a solution. Okay, but it turns out that that there's a stronger property than that. Okay, so what I'll do is I'll just take the known assumed solution and substitute it into a term on the right side, whichever one you pick for me to do, and see what happens. First of all, notice that if I plug in the assumed solution into here, the c is going to cancel out. It doesn't make any difference what multiplies these things. The same factor is going to multiply every term, so that cancels out. Okay, so pick a term. Anybody want to pick a term here? What's that? Pick any term you want here. Okay, you pick this one. How's that? Okay. All right, so you can see when I do this, all the terms are going to be the same. What I'm going to do is I'm going to plug in, I'm going to calculate J2 plus 1 mu 2 times P of J1 J2 plus 1. Okay, so that's going to give me J2 plus 1 mu 2 lambda 1 over mu 1 to the J1 over J1 factorial times lambda 2 over mu 2 to the J2 plus 1 over J2 plus 1 factorial times this constant. And now you do some obvious arithmetic. I will take the J2 plus 1 and cancel it with the J2 plus 1 factorial. So that means in the denominator for that piece, that will be J2 factorial. So the J2 plus 1 is gone. Okay, now let's see. The term in front of it remains the same. It's still J1 factorial. And I still have lambda 1 over mu 1 to the J1. So this term is that. Okay, we still have the constant, that. Now, let me write this lambda 2 over mu 2 to the J2 plus 1 as lambda 2 over mu 2 factored out times lambda 2 over mu 2 to the J2. So I have lambda 2 over mu 2 to the J2, and I factored out a lambda 1 over lambda 2. But when I do that, the lambda 1 over lambda 2 is multiplied by the the lambda 2 over mu 2 is multiplied by the mu 2. So the mu 2's cancel, and I'm left with lambda 2. And now I look at what I have here. I recognize this piece as being exactly the assumed solution. So this is lambda 2 times p of j1, j2. So what I've just shown is that if I take this solution right here and substitute it into this term, then this term turns out to be exactly equal to this term. So this one cancels with this one. But now it's easy to see that this one will cancel with this one, and this will cancel with that, and this will cancel with that, and I'm home free. So we already knew it was a solution. That is, we knew that the sum of the terms on the left and the sum of the terms on the right had to be equal, because that's what you mean by a solution. But now we see that the solution is in a sense stronger, in that the way it works is that each term on the right cancels a term on the left and vice versa. So we have a term-by-term agreement. This is called a product solution. It's a product of these two things. Okay, now you might say, well, okay, but so what? That's very nice. It works for this case, but what about other cases? The reason it seemed that this one worked is because we had an infinite number of servers. Okay, but of course that's always a boring case. What you want is a case where there's a finite number of servers, because that's when you can have blocking. So let's look at the obvious generalization of this. Okay, before I erase this, are there any questions here? All right, so the next step is straightforward, obvious. What I want to do is I want to take the case in which now, instead of having an infinite number of servers, now I have a finite number of servers. So now the same model looks like this. There's my A1, there's my A2. And now I'll assume that I have block customers cleared. So now with a finite number of servers, if an arrival finds all servers busy, then he's cleared from the system. Okay, so now what? Well, first of all, we know that whatever the probability of blocking is going to be, since we have Poisson input in the aggregate here, that means that, and each stream is Poisson, that means that each stream sees the same probability of blocking, and each stream sees what the outside observer sees. So whatever the probability is that all servers are busy, that is the fraction of customers from stream 1 who are lost, and it's also equal to the fraction of customers from stream 2 who are lost. So what I've got to do is I've got to calculate the probability that all servers are busy in this system. So when I do that, well, I'll do it the same way as before. I'll write the same equations, except that now there's a boundary condition. Now, what I'm going to say is, these equations are valid as long as J1 plus J2 is less than S. That is, as long as the total number of customers present is less than the number of servers, then on the left-hand side, there's room for an arrival to occur. That is, if an arrival occurs, then the state of the system will change. One of these J's will increase by 1. And of course, there's room for a departure to occur. On the right-hand side, if J1 plus J2 is less than S, then, well, there's certainly room for an arrival to occur in this state and an arrival to occur in this state. What about this state? If J1 plus J2 is less than S, then J1 plus 1 plus J2 is not greater than S. So that means that this state would still be there. That is, this is a legitimate state, and so this term would be there, and by the same argument, this term would be there. So what that means is that as long as the J1 and J2 are less than S, as long as I'm not on the boundary, then I have the same equations as before. Which means that if I substituted the same solution it would work in every case except possibly on the boundary. Because if it doesn't work on the boundary, then it doesn't work because it has to be the solution everywhere. So now let's look at the boundary case. So now I'm going to take the case in which J1 plus J2 is equal to S. Okay, now things are going to be a little bit different because if you look at the left-hand side, then when J1 plus J2 is equal to S, even though an arrival from stream 1 can occur, it won't have any effect on the state of the system because block customers are assumed to be cleared. So this is just like before in the one-dimensional case. When you had the state where all servers are busy, there was no rate up from that state because there was no place for the customer to go. He was cleared. So I'm going to indicate that by putting an asterisk here. So an asterisk means that if J1 plus J2 is equal to S, if I'm on the boundary, then the term doesn't appear in the equation. But otherwise it does. So on the left-hand side, there are going to be two asterisks because if J1 plus J2 is equal to S, an arrival from stream 1 or an arrival from stream 2 will not affect the state of the system. Those will be lost calls. How about the right-hand side? Well, on the right-hand side, I'll put an asterisk here to indicate that when J1 plus J2 is equal to S, this probability will be set equal to 0 because this will correspond to a state that can't occur. Because when J1 plus J2 is equal to S, J1 plus 1 plus J2 will be greater than S, and that's a physically impossible state. So when I'm on the boundary, this term will appear, this term will appear, this term will not appear, and by the same argument, this term will not appear. But now, what you see then is that for all J1 and J2 that are less than S, then the equations are just as they were before. And for all values of J1 plus J2 that add up to S, the equations are the same except that these two terms on the left are missing and these two terms on the right are missing. But you have the same solution. Because if you take this solution and plug it in, as we just showed, the solution satisfies the equations term by term. And this term balances with that term, and this one balances with that term. And so what that means is that on the boundary, you still have a term-by-term agreement because you still have this one equals this, and this one equals that, and those two terms are missing, and those two terms are missing. So you have the same solution. Of course, it's not exactly the same, but it's the same mathematical form. So what's different? What's going to be the difference here between this and what we had before? Well, before, the constant was e to the minus a1 times e to the minus a2. That was the normalization constant. Any constant will satisfy the equations, but if you want the probabilities to sum to 1, then it turns out that this would be the multiplying factor that makes everything add up to 1. Now, the normalizing constant is going to be different because, for one thing, I have a smaller number of states. I have a finite number of states, so this C would be whatever it is, so that if I add up all terms of this form, then the C would be the reciprocal of the sum of all terms of that form. So C is just the number that now makes everything add up to 1. So it's a different C. So the numerical values of the probabilities are going to be different, but the formula is going to be the same. Okay, so now this raises a question. What we just proved was that the product solution still works. So if I have a finite number of equations, finite number of states, then the probability is given by this product. The state probability is given by this product, where the product is that, is that times that, or this times this, where this is given by this times a constant, not the same constant, but something else. This is given by this times some constant. And so I again have the state probability given by the product of those two terms. So now let me ask this question. Everybody knows that two random variables are independent if and only if, I think, the joint distribution is the product of the marginal distributions. Right? So did I just prove that the two random variables that correspond to the number of calls from stream 1 and the number of calls from stream 2 are independent? Because if I did, then I just proved something incredible, because if I have a finite number of servers, then the number present from each stream cannot be independent of the other. For example, if you had 10 servers and I told you that 9 servers are busy from stream 1, then you would know that the number of customers present from stream 2 could only be 1 or 0, but couldn't be any more than that. So you have a hard constraint here, which is the sum of the number of customers cannot be greater than the number of servers. And yet, I just proved, or did I, that the random variables are independent because the joint probability is the product of the marginal probabilities. So is the definition of independence wrong? Or did I pull a fast one on you, or what? Anybody have a clue here? Everybody agree that they are dependent? Or did I prove that they're independent even though it seems that they're dependent? Well, to end the suspense, it's true that I have a product here, but it's not true any longer that this part is the marginal distribution of the number from stream 1, and this part is the marginal distribution of the number of stream 2. What I have to do is I've got this C, and I would have to split my C up into a product C1 times C2, such that the C1 times this part would be the marginal distribution of the number from stream 1. And it isn't. They can't do that. It's not true because they're not independent. So the trick here, to the extent that there is a trick, is that yeah, I do have a product, but the terms in the product are not the marginal probabilities unless we have an infinite number of servers. In that case, then each term itself represents the probability that describes that stream alone. But in the other case, it simply is a product. But it doesn't necessarily mean that the first term in the product represents the probability for the first stream, and the second term represents the probability for the second stream. OK, but in any event, we now have a complete solution to this problem, because if I ask you for the probability of being in any state, then you could calculate it by using this formula and just find the value of C that makes everything add up to 1. But generally, I may not care how many customers there are of each type. What I really want to know is what is the probability that the total number of customers present is a certain number. In other words, what I want to do is define Pj to be the sum of P of J1, J2 over all values of J1 and J2 that add up to J. And in particular, of course, I want to calculate PS. Excuse me. So PS is the sum of the probabilities, J1 plus J2 is equal to S, which is the fraction of time that all servers are busy, which is also for each stream, because they're both Poisson streams, it's the fraction of customers who find all servers busy. So it's the probability of loss for each stream. So the question is, what is it? Or equivalently, let's see if we can get a formula for this. OK, so let me rewrite this piece right here. I'll say Pj is equal to the sum of A1 or let's say I'll write it like this. A1 to the k over k factorial, A2 to the j minus k over j minus k factorial times this constant as k runs from 0 to j. Okay, so probability being in state j is the probability of k customers from stream 1 and j minus k from stream 2 summed over all values of k. So it adds up to j. And now all I got to do is evaluate that sum. Okay, but now I'll do it like this. Let's see, what I'm going to do is I will multiply by j factorial and divide by j factorial. And then recognize that this piece here, that's exactly the binomial coefficient j choose k. Right? J choose k is j factorial divided by k factorial times j minus k factorial. So with that observation, it should become obvious, because what I'm left with is c times 1 over j factorial times the sum of j things taken k at a time, a1 to the k, a2 to the j minus k, as k runs from 0 to j. Anybody recognize this sum? Right, that's just the binomial expansion of a1 plus a2 to the j. Okay, it's by the binomial theorem. So Pj is equal to a1 plus a2 to the j over j factorial times the constant. But what's the constant? Well, the constant is whatever it takes to make these probabilities sum to 1 for j equals 0, 1, 2, up to s. So that means that that constant is 1 over the sum of terms of the same form, a1 plus a2 to the k over k factorial as k runs from 0 to s. Okay, if I make the denominator this, then if I add these things up as j runs from 0 to s, the numerator and denominator will be equal, and I will get 1. So that's how I get the normalization constant, the c. This term right over here. And of course, that c does not factor into two c's, two separate c's, each of which then makes the factor a marginal distribution. Okay, so this is my answer. In particular, when j is equal to s, then what do I get? Okay, what is P sub s? Well, it's the Erlang-B formula. This is just the Erlang loss distribution with a replaced by a1 plus a2. The probability I'm in state j is something to the j over j factorial divided by a sum of terms just of that same form. So in particular, when j is equal to s, this is simply the Erlang-B with s servers and a1 plus a2 Erlangs. So not only did we give an example in which it was necessary to write rate out equals rate in, multidimensional state equations, as opposed to one-dimensional. Furthermore, in that example, we had a product solution, even though we didn't have an infinite number of servers. And in addition, we got a theorem out of it in this case, which says that if we have a system of servers with two Poisson loads, in which the loads, the arrivals occur according to independent Poisson processes, and the block customers are cleared, and the service times in our model, we said, although we can, as you can see in a moment, we can drop this, are exponentially distributed, but with different averages, different mu's. Then the probability of blocking for each stream is exactly the same, and it's exactly what I would get if I simply took the ordinary one-dimensional Erlang B and took as the load the sum of the loads. Despite the apparent nonlinearity of this, there's a linearity in the sense that multiple streams just add. So if I had a Erlang loss system with any number of streams, A1, A2, and so on, then the state probabilities for this system, as long as block customers are cleared and as long as the streams all arrive according to independent Poisson processes, the state probabilities are simply exactly what you got before, except that you replace the offered load by the sum of the offered loads. The offered loads in Erlang simply add, regardless of whether or not the service times are the same, come from the same distribution. And from that it seems, and we'll prove later, that what that seems to imply is that it doesn't matter what the service time distribution is. Because if I have customers arriving and these guys are exponential with one mean, and these guys are exponential with another mean, so that on the servers they're mixed up, even though they come from exponentials, the resulting distribution is the mixture of exponentials, which is not itself exponential. Which means, from which you might guess that the answers do not depend on the distribution of service times, which of course is our amazing theorem. I haven't proved it yet, but this is more evidence that the theorem is true, that the service time distribution doesn't matter as long as I have Poisson arrivals and as long as I have block customers cleared. So there's a whole lot of things going on in this problem. Now this is pretty powerful, pretty amazing actually. And this is an illustration, I think, of queuing theory's ability to trick you. Because let's suppose you're an engineer, you're a telephone engineer in the old days. Remember that people were doing this since the early 1900s, before probability and stochastic processes even had a firm foundation. They were using these formulas. And so what would you do if you're an engineer and someone said, well, I've got this Erlang loss system, but I've got two separate loads. How do I handle it? And your answer would be, well, I don't know, but if I had to make an approximation, the best thing you could hope for would be just add the loads up. Of course, it's wrong, you would think, but it's as good as anything because I don't know how to do it. And the answer is, well, it's not wrong, it's exactly right. So what queuing theory does is it lulls you into this false sense of security. So we'll see at the beginning, it says, whatever you want to do, you want to add things, you want to combine Poisson streams, you want to ignore the service time distribution, you want to interpret the probabilities as being the same even though they're measured from different viewpoints. Don't worry, go ahead, do it, it's all going to work out in the end. Everything that you would like to happen, happens. So just when you're sitting back and saying, man, this is a piece of cake, then all of a sudden things that you think are obvious turn out to be false. Okay, any questions about that? In a textbook, I just did the section called section 4.2, or at least half of it. So I just derived, in fact, equation 2.11. That's this here, right there. That's 211. And ready to look at an exercise. So any questions about this? Okay, so let's look at exercise number 2. Now, part of my point here is that this stuff seems to work because it's a trick. And in a sense, that's true. It is a trick. It doesn't work in every case, but it tends to work in more cases than you might think at first glance. Okay, so let's look at a simple model of a telephone network, a circuit switch telephone network. So here's the network. I have 3 cities. Here's city A, city B, and city C. And I have communication channels, or trunks, S1 trunks connecting AB, and S2 trunks connecting BC. So this is like a simple telephone network, because in this network, if I want to make a call from A to C or from C to A, then I'll allow that call. What that means is that I have to simultaneously have a trunk available in group 1 and a trunk available in group 2. And then when a call arrives, if it can find the trunk in both groups, then a circuit is set up. And that a trunk in group 1 and a trunk in group 2 are reserved for this customer for the length of the conversation. And then when the conversation ends, when the subscribers hang up, then each of these trunks becomes available. So if we didn't allow calls between A and C or C and A, then these would be 2 single independent Erlang loss systems. But we're going to assume that that they're not, that they interact. So this is the simplest, non-trivial circuit switch network. Circuit switch means that when you make a connection, here's the network. You got all of these nodes in the network. And in the circuit switch network, when you make a connection, then you set up the connection for the length of the call, and then when the call is finished, you drop the connection. That's the definition of circuit switched, as opposed to packet switched. So for voice communications, traditionally, you use circuit switching. You set up the path, and then that path is dedicated to the subscribers for the length of their conversation. For data, you don't need to be able to make the connection in real time. So there what you can do is you can form your data into packets, and you can send the packets from here to here, and then they can wait around, and then they can go to the next node, and then the next node, and the next node, and so forth. So with packet switching, you don't do it in real time on the one hand, but on the other hand, you don't have to set up a complete circuit and hold it for the length of the conversation. You can pick your route as you go along. And so modern networks now, the question is, how can we engineer these networks so that they can handle both circuit switching and packet switching, or how are we going to combine voice and data and all kinds of other traffic, multimedia, all that jazz. Okay, so this is the starting point. Okay, so what I'm going to do is define state probability. And now for this case, I need 3 variables to describe what's going on. J1 will be the number of calls between A and B, single trunk calls. J2 will be the number of calls between B and C, and those are single trunk calls. And J3 will be the number of calls between A and C. So each of these calls holds 2 trunks simultaneously. And now, as before, I'll write rate out equals rate in. Of course, the equations are going to be more complicated than before. Then I'm going to solve them, but it'll turn out that I get the same solution. Every problem I look at has the same solution. Okay, so first of all, I'll start by writing the rate out of this state. And of course, there's boundary conditions here. So the first boundary condition is that J1 plus J3 is less than S1. J1 is the number of calls between A and B, and J3 is the number of calls between A and C. And so J1 plus J3 is the total number of trunks that are busy in group 1. So I'm going to take the case in which J1 plus J3 is less than S1, which means that there's room for a new call to arrive. And similarly, J2 plus J3 is less than S2. J2 is the number of calls going between B and C, and J3 is the number of calls going between C and A. Okay, so these trunk groups, the the states of these trunk groups are not independent of each other because they're linked in a sense by the calls between A and C. Okay, now, under those boundary conditions, what is the rate at which I leave this state? Well, an arrival from stream 1 will cause this guy to increase by 1. And an arrival from stream 2 will cause this guy to increase by 1. And an arrival from stream 3, that is an AC or CA call, will cause this guy to increase by 1. And there's room for each of these increases because by the boundary conditions, there's at least one trunk idle in each of the two groups. Okay, how about departures? Well, ordinarily, if these are telephone conversations, you would expect that the mu's would all be the same. The average service time would be the same. But it turns out to be simpler to assume here that the customers from stream 1 have exponential service times, although again, we can remove that requirement. But the service completion rate will be mu1 for these guys, mu2 for these guys, mu3 for these guys. So we don't even have to assume that they're from the same population, although in most applications, I guess they would be. So here's J1 mu1 is the service completion rate for calls between A and B. J2 mu2 for calls between B and C, and J3 mu3 for calls between A and C. And now we have to equate that to the rate at which I enter this state. So I can enter the state from below by arrivals or from above by departures. So everything is the same as before. So I'm going to get lambda 1 p of J1 minus 1, J2, J3, plus lambda 2 p of J1, J2 minus 1, J3, plus lambda 3 p of J1, J2, J3 minus 1. That represents the rate at which I enter this state by having arrivals. But I could also enter it by having departures. J1 plus 1 mu1 p of J1 plus 1 J2 J3 plus J2 plus 1 mu2 p of J1 J2 plus 1 J3 plus J3 plus 1 mu3 p J1 J2 J3 plus 1. Okay, so I got rate out equals rate in. You can see that if you compare where we were half an hour ago, we're really writing down complicated things. This stuff looks like it's getting complicated very fast. But the form remains constant. So all we're doing is making things look more complicated. Of course, you have to formulate things correctly. The key here is to recognize that I need one variable, and one variable only, for the number of calls between A and C. I mean, the natural way you might do this before you get the knack is you might say, well, I'll let J3 be the number of calls between A and B that are also holding a trunk in C. And then I'll let J4 be the number of calls between B and C that are also holding a trunk in group between A and B. Then I have 4 variables. It looks like that would be simplest, but actually it's complicated. In fact, it's impossible. You have to formulate the thing correctly. All right, now I've got to solve the equations. Well, I'm off the boundary, so it's easy, because now you know immediately from what you saw before that if I plugged in this formula, it would work. Lambda 1 over mu 1 to the J1 over J1 factorial. lambda 2 over mu 2 to the j2 over j2 factorial, lambda 3 over mu 3 to the j3 over j3 factorial times a constant. Because these equations are of the same form as before, except that there are 3 variables instead of 2 variables. Of course, the diagram looks much different. That's part of the interesting thing here, is that physically the system is much different from what I had before. But in terms of the structure of the states, it's the same. So I have the same equation, so I'm going to get the same solution, except that we don't know whether the solution really applies, because we know that it's going to apply off the boundary. But what if I'm on the boundary? It has to apply everywhere. But we make the same argument as before. Let's say that I'm on the boundary. Let's take, for the sake of argument, where we're going to allow this to be equal. If j1 plus j3 is equal to s1, then this term will not appear because the customer from stream 1 will be cleared from the system. Okay, so that's gone. That's the asterisk. How about this guy? Well, he can still be there because j2 plus j3, which is the total number of customers here, is less than s2, so there's room for him. So this would be in, but this guy would be out, because if j1 plus j3 is equal to s1, all of these trunks are busy. So if a call wants to go between A and C, it would be cleared. It would be lost call, because even though there's a trunk available here, there's not one available here, and it has to have a trunk available, 2 trunks simultaneously, one in each group, in order to be a carried call. So I'll put an asterisk there. Okay, these guys, no problem, same as before. There's room for them to leave. Now, if you look on the right-hand side, we make the same arguments as before, namely that, well, if j1 plus j3 is equal to s1, then this probability must be 0, because this represents a state that's physically impossible, j1 plus 1 j3. So we'll put an asterisk here, and there would be an asterisk here. Again, j1 plus j3 plus 1, but this one's OK. And now we ask how we solve these equations. And the answer is, well, it's the same solution as before. Because what's going to happen is, when I plug in the product solution, this term will cancel with this term, and this term will cancel with this term. And everything else will have a term-by-term agreement. And now you can see that, well, yeah, it's going to work here. It's going to work here, too. It just moves the asterisks around. And in fact, if I was on the boundary where j1 plus j3 is equal to s1 and j2 plus j3 equals s2, that means everything is busy, then all the lambdas would have stars on them, and these 3 terms here would all have stars on them, and I would have this rate down and this rate up, and it would still work. So the bottom line is that we again have a solution. Here it is. It would be easy for me to calculate the solution now, because I could write a program that calculates recursively, because of these nice forms, all of these terms and puts them in memory. Let's say take C as being 1. And then when I've calculated every one of them, I just divide each of them by the sum of them. And that normalizes, and now I have an array in which I have the state probabilities. And from that I can calculate the performance measures. OK, we're out of time. So next time I'll start here. We'll continue with this problem. And I'll talk more about calculating these performance measures, and then go the next step, which is to look at something that instead of a circuit switch network is in fact a packet switch network, which looks completely different and incredibly turns out also to have a product solution. OK, so we'll start there next time.